In this video, we're going to consider our last two possible terms, our quadratic zero and our quadratic pole. We're going to spend more time sort of deriving the quadratic zero Bode plots, and then we're just going to say it's similar for our quadratic pole, and we're not going to show all of the details for that. So our quadratic zero is this big monster up here in the top right of the screen. And so before we get started, what we want to do is sort of simplify that a little bit and see if we can't get it in a more familiar form where we have something that looks like a plus jb. And so looking at this, we note that in this far right term over here, we're going to end up having a j squared term. So recall that j is of course square root of -1, so that means that j squared is equal to -1. So with that in mind, we can sort of rewrite that equation above, and we can say, let me zoom out there. So we can say that we have our a component, which is going to be the 1 minus our omega over omega sub k squared. So all of that is sort of like our a, and then we have plus j times our b component, which is the 2 zeta 1 omega divided by omega sub k. So we have something that looks like this. So again, we have sort of our a component is here, and our b component is here. And so notice what's different here compared to all the previous ones we've seen is now we have an omega term in both the real part as well as the imaginary part. So let's take a closer look at our magnitude. Or actually, instead of doing that, let's go ahead and do what we did in our last video, and let's go ahead and put this in polar form so that we can kind of see our magnitude and phase at first, and then we will look at each one of those in turn. So convert to our polar form to more easily see our magnitude and phase. So our magnitude is just going to be the square root of a squared plus b squared, but of course now we have sort of a whole big mess here. So we have the square root of 1 minus the quantity omega divided by omega k squared. So all of that is going to be squared, plus our b squared, which is 2 zeta 1 omega over omega k. Okay, so that is our magnitude, so we're not going to take that down any further. And then also, we can find our phase angle. So that is going to be magnitude angle with inverse tangent. And in the numerator, we're going to have our b, which is the 2 zeta 1 omega divided by omega k. And in the denominator, we have 1 minus omega divided by omega sub k quantity squared. Okay, so that at first glance doesn't really help much. We still have a big mess, but let's look at each one of these sort of one at a time. So let's start with our magnitude, which is over here on the left. So starting with our magnitude, because we can't really make that any simpler, we're going to do what we've done in the past, and let's say, let's consider sort of some extreme cases. So let's say what happens as our omega is going to 0. Well, as our omega goes to 0, we can see we have an omega here and then omega here, so both of those terms are going to go away, and we're just going to be left with square root of 1, square root of 1 squared, not that it really makes much difference. So what we're going to get then is that our gain in decibels is equal to 20 log of 1, which is equal to 0. Okay, so we sort of have a data point there. So we can say for really, for low values, we're going to have 0. And so we'll go up and we'll update those plots in a little bit. So the other case is we can say, well, what if our frequency gets really high? What if our omega goes towards infinity? And so what we can see is that there's going to be one term in particular that becomes dominant. So we have this omega, which is squared, and then that's squared, so that's going to be an omega to the 4th, and then over here we have an omega squared. So what's going to end up happening is that omega to the 4th is going to dominate everything else as omega gets large. So we can say that our gain in decibels is equal to 20 log, and now we're just going to keep that dominant term because everything else sort of gets overshadowed by that. So that's going to be negative omega to the fourth. Sorry, that fourth is on the outside of the negative sign there. So we get negative omega to the fourth. Of course, we can see that that fourth is going to take away the negative sign, and we're going to have we're going to have 20 log of omega squared. So taking the square root of omega to the fourth, we get omega squared. Now we're going to bring down the exponent, use our log properties, and we can say this is equal to 40 log of omega. So now this looks really similar to our simple zero. So similar to our simple zero. The main difference is, of course, we have now this 40 out front as opposed to 20, so we're going to have a slope of 40 dB per decade. And the other difference is we're going to have a corner frequency or breakaway frequency of omega sub k. So let's come up here to our gain plot and let's label some frequencies. So let's say right here we have our omega sub k as our corner frequency, and then we can go 1 decade to either side. So if we have 1/10 of omega k here and 10 times omega k here, what we're going to see is we're going to have a steeper increase in that gain than for what we saw for our simple zero. Okay, so we have something that looks like this, and if we use that same piecewise linear model, which remember is an approximation, so it's not exact, but it gives us a good first order approximation. We say for really small frequencies, and we're going to approximate, we say less than omega sub k, that gain is 0 decibels. And then we're saying after that point, it's increasing at a rate of 40 decibels per decade. So the slope of this line would be positive 40 dB per decade. And so again, as I've indicated here, that just keeps on going upward and to the right. Okay, so now let's figure out what's going on with our phase. So for our phase, we're going to be looking at this component here, and so let's actually just bring that down with us to make this a little easier. So let's put that here. Let's put it over here actually. Okay, so we've got that, and so now we're going to consider our phase. So this is our phase here. And so again, what we're going to do is sort of consider our various cases. So if we consider what happens when omega is equal to 0, well, we see we have omega here, so that top term is going to go to 0. This is going to go to 0, but that doesn't really matter. Really, we focus on that top one going to 0, which means we have inverse tangent of 0. So for the case of 0 frequency, our phi is going to be 0 degrees. So what if we have the case of it equal to the corner frequency? So omega equals omega sub k. So in this case, again, we have sort of our two frequencies to consider. We have this frequency in the numerator, which is going to be omega k, and this frequency in the denominator. So in this case, we're actually wanting to focus more on this omega in the denominator. So if we have omega divided by omega, that's going to be 1. So 1 minus 1 squared is going to be 0. So we have inverse tangent of something over 0, which in the limit is going to go to 90 degrees. So we have phi equals 90 degrees for the case of omega equals omega k. And then our third case is we can say, well, what happens as that frequency gets really large? What happens as it goes to infinity? And so in this case, probably the best way to think about it is to come back up and look at sort of this simplification here, where we reduce this to sort of be an a plus jb. And so remember, if we look at our complex plane, so this is our real and our imaginary axis, we have a plus jb is somewhere here. So this would be point A, this would be point B. So what happens if that omega gets really large? So let's get rid of some of this. And so just like we talked about with our magnitude, the term that's going to end up dominating is this omega squared. So it's going to end up overshadowing this omega, and of course it's going to end up overshadowing this 1. So what that means then is that our a is going to get really, really large compared to our b. So in the limit, this point is coming down here, and it's going to be essentially on our axis, which corresponds to an angle, and sorry, I'm saying that wrong. So it won't come down to that axis, but because we have this negative sign out front, it's actually going to be coming down this way, and that's going to correspond to an angle of 180 degrees. So this corresponds to a phase of 180 degrees. So again, this is similar to what we saw for our simple zero, so we can do the same straight line approximation. So coming up here, let's mark our 3 sort of key frequencies. Let's say we have our corner frequency omega k. We have 10 times omega k 1 decade up, 0.1 omega k 1 decade down. Our key frequencies, or our key phases now are going to be 90 and 180. So 90 degrees and 180 degrees. And so we're saying it's going to be 90 degrees at that corner frequency and 180 degrees at a decade above that. And so remember, just like with our simple zero, we're saying if it's below 1/10 of our corner frequency, our phase is 0. At the corner frequency, the phase is 90. And for 10 times the corner frequency and above, the phase is going to be 180 degrees. And so we're just going to use a straight line approximation in between there in order to get our Bode plot. And so again, keep in mind that these are approximations. So in this case, we have a slope of 90 degrees per decade. Okay, and so one other thing to mention that we'll hit on a lot more in control systems, but we have this variable that's been floating around and I've not really addressed it, and that's this zeta term here. And so what this is this is our damping ratio. So if you look on page 620 in the textbook, what you can see is that the amount of variation from this blue line approximation is going to depend on the value of this zeta term. And so this zeta term, I think I said, but let's write it, is something called our damping ratio. So just something to keep in mind. Okay, so as promised, we're not going to go into all of this detail for our last potential item, our quadratic pole, but I've copied what it looks like here. So the same thing as our quadratic zero, we just have to the power of -1 because of course it's in the denominator. And I've also switched this to be omega sub n because we're talking about a different corner frequency. So we can see it looks exactly the same as a quadratic zero, except our slopes for our gain is now -40 dB per decade as opposed to positive. And our slope here is in our phase is -90 degrees per decade as opposed to positive 90 degrees per decade. So that covers the 7 different terms that we can see. So if you look on Canvas, there's a good summary. There's also a summary on page 621 in the textbook. There is a slight error in one of the forms for the simple zero. That's corrected on Canvas. So corrected on Canvas. And so that's useful because not only does it show kind of what we had, but if you think back to that first video, the second one where we're looking at the second term, our pole or our zero at the origin, we sort of generalized it if we had to the power of n. And so what these summary tables do is they generalize each of these 7 terms in terms of what if you have that to the power of n. So it's a very good general guide that you can use as you're solving these problems. So in subsequent videos, we're going to look at some examples on how to make Bode plots, but just really briefly, we want to talk about the general procedure for making these Bode plots. So the first thing you want to do is you want to mark your corner frequencies. And so we've of course just talked about what our corner frequencies are. That only applies to certain terms. The second step is going to be to sketch the plot for each component individually. So sketch plot for each component or each term individually. And then the third step is just going to be to add all components together to get our overall Bode plot. So what is that Bode plot? That's going to be our Bode plot for the transfer function of the circuit, or sometimes maybe we're just given a function to start with. So again, that probably seems kind of vague at the moment, but hopefully knowing those 7 terms and how to plot them individually, you kind of have an idea. And then, like I said, we're going to look through a couple examples in the following videos, and we're going to get a better idea of how to actually apply this.